Something crossed our solar system in 2017. It came from outside, from between the stars. It moved faster than anything we'd ever tracked. And then, when it should have been slowing down, it sped up, not because of the sun, against it. Every natural explanation anyone has tried has at least one thing nobody can make fit. And one of the most respected astrophysicists alive, a Harvard professor with 2 decades of peer-reviewed work behind him, published a paper suggesting it might not have been natural at all. One confirmed interstellar visitor in all of recorded history, and we still don't know what it was. There's a telescope sitting on the summit of a Hawaiian volcano. It doesn't look for alien signals. It doesn't listen for radio transmissions from distant civilizations. What it does is more practical, and, as it turned out, far more important. Every single night, it sweeps the sky in a slow, methodical grid, cataloging everything that moves. Asteroids drifting through the inner solar system, comets on long loops around the sun, anything that might, one day, come close to Earth. The telescope is called Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, built and operated by the University of Hawaii's Institute for Astronomy. It can scan 3,000 square degrees of sky in a single night. It has catalogued hundreds of millions of objects, one of the most powerful asteroid hunting instruments ever built. On the night of October 18th, 2017, Pan-STARRS did what it always does. It swept its section of sky and recorded everything it saw. Millions of data points, terabytes of images. The next day, a Canadian astronomer named Robert Werrick was processing those images, moving through them one by one, looking for objects that had shifted between frames, the standard way of finding anything moving through the solar system. And something caught his eye, a faint smear of light, moving at the wrong angle, the wrong speed. He ran the orbital calculation, the routine, and the output stopped him cold, because the trajectory wasn't an ellipse. Every object in our solar system, every planet, comet, asteroid, every drifting grain of dust, follows an elliptical path around the sun. That's been true without a single exception since we started looking up Kepler's first law, 4 centuries of observed reality. This object was on a hyperbola, a trajectory so steep, so fast, that no amount of solar gravity could have produced it. The math said it couldn't have come from anywhere in our solar system. It came from somewhere else. In 400 years of modern astronomy, nobody had ever confirmed an object from interstellar space moving through our system. This was the first one, and it had already made its closest pass to the sun 3 weeks earlier, already leaving. We had at most a few weeks before it would be too faint for any telescope on Earth to see. The astronomical community moved fast. Observatories around the world swung their instruments toward the coordinates. The European Southern Observatory in Chile, the Very Large Telescope, Keck in Hawaii, Gemini North, the best eyes on the planet, all pointed at one faint dot. They had limited time. Every hour, it was getting fainter, farther away, moving. What they found over the following days was at first almost underwhelming, and then slowly, with each additional data point, increasingly strange. First, no coma. When a comet approaches the sun, heat causes surface ice to sublimate, to turn directly to gas, skipping the liquid phase entirely. That gas expands around the nucleus into a visible halo called a coma. Every comet we've ever observed has one. It's how you tell a comet from an asteroid at a distance. Oumuamua had nothing. No halo, no outgassing. They checked for water vapor, carbon dioxide, carbon monoxide, every volatile compound they knew to look for. Nothing. Fine. So it was an asteroid then. A rock from another star. Strange but not impossible. Theorists had predicted that planetary systems should eject debris, and some of it should pass through other systems eventually. We just hadn't caught one before. And then they looked at the light curve. When an object rotates in space, its brightness changes as different faces catch sunlight. A perfect sphere barely flickers. A rough, irregular asteroid might vary by a factor of 2 or 3. A very elongated object, a cylinder, say, could vary more. Oumuamua varied by a factor of 10. Every 7 to 8 hours, it went from dim to blazing bright and back, 10 to 1, cycling through that range with disturbing regularity. Think about what kind of shape does that? Something radically stretched in one direction, so extreme it can nearly vanish when it's pointing edge-on at you, and blaze like a flare when it rolls its broadside into the sunlight. The models landed on proportions of roughly 10 to 1. Some estimates pushed further, somewhere between 400 meters long and 40 wide if it was a cigar, or wider, flatter, thinner if it was more like a pancake. If it was the cigar shape, it was the length of 4 football fields, the width of a small apartment building. No natural object in our solar system has proportions like that. Not one, not even close. The scientific community's initial reaction, unusual but explainable. Maybe a fragment torn from a larger body by its home star's gravity, tumbling into the void. Rocks can be oddly shaped. We just hadn't catalogued enough interstellar objects to know what normal looks like. That was the working assumption. Then they took another look at the trajectory data. The working assumption collapsed. I need to stop here for a second, because what comes next only lands if you understand the physics underneath it. When an object moves through the solar system, every force acting on it is calculable. Gravity from the sun, small perturbations from nearby planets, the faint but real pressure of sunlight. We account for all of it. This math is not approximate. We used these same equations to navigate Voyager 1, launched in 1977, to within a few kilometers of its predicted position after traveling more than 23 billion kilometers from Earth. tested for decades, at scales that leave no room for error. When we track an object and calculate where it should be, we expect to find it exactly there. Astronomers tracked Oumuamua from October 19th until it became too faint to observe in early November 2017. 11 days of data, position measurements from multiple independent observatories. When they compiled all of that and ran the best fit orbital solution, they found a discrepancy. Oumuamua was not where pure gravity said it should be. Not by a tiny margin, not instrument noise, a real growing gap, statistically significant and getting wider with every observation. The object was accelerating, faster than the sun's gravity could account for, faster than any known force on that trajectory should be pushing it. It was leaving at about 87 kilometers per second by the time it faded from view. 3 times Earth's orbital speed, still gaining. We have a name for this kind of thing, non-gravitational acceleration, and we know what causes it in every previous case: comets. When a comet passes near the sun, the surface ice sublimates into jets of gas that stream away from the nucleus. A tiny thrust, small but measurable. It shifts the comet slightly off its purely gravitational path, so Oumuamua is accelerating non-gravitationally. The explanation that fits is outgassing, except the world's most sensitive spectroscopic instruments had been pointed at Oumuamua for days, looking for any trace of outgassing. Water, carbon dioxide, carbon monoxide, cyanide, anything. They found nothing. No coma, no gas, no dust, no jet, no trace of activity whatsoever. The explanation that perfectly fits the trajectory data is flatly ruled out by the spectroscopic data. When that happens in science, when the answer to one problem is directly contradicted by the answer to another, you don't pick your favorite and move on. You go back to the beginning. The beginning for Oumuamua was disturbingly empty. The paper formally documenting the non-gravitational acceleration was published in June 2018 in the journal Nature. Lead author Defied at NASA's Jet Propulsion Laboratory, with co-authors from observatories across the world, 12 authors, multiple independent datasets, 6 different telescope systems. The anomalous acceleration was not a measurement error, not a modeling error, real, and no one had a good explanation for it. That's when the theory started. Three serious scientific proposals came out of the astronomical community. 3 attempts to explain what happened without invoking anything outside a physics textbook. Each one comes close. None of them quite makes it. In 2020, astronomers Darryl Seligman at the University of Chicago and Gregory Laughlin at Yale published a paper proposing something elegant. What if Oumuamua was made mostly of molecular hydrogen ice? Not water ice, not carbon dioxide ice, hydrogen ice. Solid molecular hydrogen, which forms at temperatures near absolute zero, around 14 Kelvin, roughly negative 259 degrees Celsius. Temperatures found deep in the cores of dense interstellar molecular clouds. Here's the part that makes it work. When hydrogen ice sublimates, when it turns from solid to gas in the warmth of the inner solar system, it produces hydrogen gas, and hydrogen gas is nearly transparent to visible light, almost undetectable by standard spectroscopic instruments. If Oumuamua was a hydrogen iceberg, it could have been outgassing the entire time we were watching it, providing exactly the thrust that explains the trajectory anomaly, and our instruments would have missed it entirely, because hydrogen is invisible in the wavelengths we were looking at. One mechanism, two problems solved. Clean, elegant. But hydrogen ice is fragile, cosmically fragile. Interstellar space is not empty. It's threaded with radiation, cosmic rays, UV from distant stars, a persistent slow bombardment of high-energy particles that have been streaming through the galaxy for billions of years. That radiation erodes a hydrogen iceberg, sublimating the surface gradually over millions of years, even in the cold dark between the stars. The nearest star systems to ours correspond to travel times of millions of years at interstellar velocities. For Oumuamua to have arrived with enough hydrogen ice left to produce the observed acceleration, it would need to have started its journey at a very specific size, large enough to survive the erosion, small enough that we could still see it. A narrow window, and the more carefully you run the numbers, the narrower it gets. Not impossible, but the probability is low enough that most researchers don't think it holds. The hydrogen iceberg answered the questions. It just raised a harder one. Is any of this statistically plausible? Most researchers concluded, probably not. In 2021, Stephen Desch and Alan Jackson at Arizona State University pointed to a different kind of ice, nitrogen. Solid nitrogen exists on the surfaces of cold Kuiper Belt objects and their equivalents in other solar systems. Pluto has vast plains of nitrogen ice on its surface, confirmed in 2015 by NASA's New Horizons mission. Now imagine a large impact on a Pluto-like world in some distant solar system. A planetary collision billions of years ago in a system we've never seen. The impact ejects a fragment of the icy surface into space, a thin, flat shard of nitrogen ice spinning slowly, drifting outward through the outer solar system of its birth star and eventually escaping into interstellar space. Nitrogen ice does sublimate in sunlight, more slowly than water ice, more quietly, without producing the kind of visible coma that spectroscopic instruments easily detect. And here's what Desch and Jackson pointed out. The color of Oumuamua, a reddish tone detected in early photometric observations, is consistent with aged nitrogen ice that's been exposed to cosmic radiation over millions of years. Color match, sublimation rate that explains the acceleration, no coma to contradict the spectroscopy. This hypothesis got more traction than the hydrogen version, more physically grounded, more observationally supported, but it has a problem, a big one. For this to work, nitrogen ice fragments need to exist in sufficient numbers for one to plausibly pass through our solar system within human history. How many would that require? The models suggest approximately 10 to the power of 26, 100 septillion objects, 10 followed by 26 zeros. Current models of planetary formation suggest that number is orders of magnitude higher than what any known population of exo-Kuiper belt objects could plausibly produce. You'd need every planetary system in the Milky Way to have ejected far more nitrogen ice fragments than the physics of planetary collisions allows. Not impossible, but the math demands an abundance that simply isn't there. Two theories, two problems. Neither one holds under scrutiny. A third category of explanation drops the ice entirely. Some researchers propose that Oumuamua wasn't a solid object at all. It was an aggregate, a loosely bound, extremely porous cloud of dust particles held together like a three-dimensional snowflake with almost no internal density. Why does that matter? Because radiation pressure, the actual physical push of sunlight on any surface, can accelerate an object if that object has enough surface area relative to its mass. Lower the density, and the effect gets bigger. The math of radiation pressure is real and well understood. We've built spacecraft designed to exploit it. Japan's Icaros demonstrated it in 2010. The Planetary Society's LightSail 2 operated on the same principle. For radiation pressure to explain Oumuamua's acceleration, the object would need a density lower than any solid object ever observed in our solar system. Less than 10 times lighter than aerogel, the least dense solid material humans have ever made. Essentially a dispersed cloud of particles that somehow held together as it passed through the inner solar system. No model of planetary formation produces anything like that. No observational data suggests such objects exist in numbers sufficient to explain an interstellar encounter. But this last theory did open something, a door. An uncomfortable one, because radiation pressure on a very thin, very flat object can absolutely explain the acceleration, if the object is thin enough, flat enough, and, crucially, artificial. In November 2018, nearly a year after the discovery, two researchers at Harvard submitted a paper to the astrophysical journal Letters. One was Shmuel Bialy, a postdoctoral researcher. The other was Avi Loeb, at the time the chair of Harvard University's astronomy department. One of the most cited astrophysicists in the world, not a fringe figure, not a podcaster, a career scientist with 2 decades of peer-reviewed research behind him. Their paper asked one question: if radiation pressure explains the anomalous acceleration, what does the geometry of Oumuamua have to be? They ran the numbers. For radiation pressure to produce the observed acceleration at the object's estimated mass and distance from the Sun, Oumuamua would need to be extraordinarily thin, between 0.3 and 0.9 millimeters thick. Less than 1 millimeter, hundreds of meters wide. There is no known natural process that produces an object with those proportions. No impact, no tidal disruption, no cometary fragment. Nothing in the catalogue of solar system, or planetary science. So Bailey and Loeb said the thing everyone had avoided saying: what if it was manufactured? Not necessarily a spacecraft, not necessarily occupied. Their language was measured. Two possibilities: an operational light sail, a technological device using solar radiation for propulsion the way actual solar sail spacecraft do, or derelict technology, wreckage from a civilization that might not exist anymore. They also noted that Oumuamua's trajectory suggested it had been moving at a velocity consistent with the local standard of rest, meaning that for most of its history, it wasn't going anywhere in particular relative to nearby stars. It had been drifting, essentially stationary in galactic terms. Loeb put it plainly: it resembled an object that wasn't headed anywhere specific, something adrift, a message in a bottle from a civilization that threw it before we existed. Now, what Loeb did and didn't say matters here. He didn't claim this was definitely alien technology. He ran the math on a hypothesis, found it wasn't ruled out by the data, and published it. He invited criticism. He wanted to be proven wrong with better data, or proven right with better data. That's how science is supposed to work. What happened instead surprised a lot of people who'd been watching. Senior astronomers called the paper embarrassing, sensationalism, irresponsible. One prominent researcher said it brought ridicule to the field. Another called it a hypothesis of last resort. Loeb's response was patient and specific. He pointed out that his paper proposed a testable hypothesis, one that made predictions, one that could be confirmed or refuted with better data. And he pointed out what the critics hadn't answered. What is the alternative? If not a light sail, then what? The three natural hypotheses all have serious documented problems. The community was effectively saying, we don't know what it is, but we're certain it's not that. That's not a scientific argument.
It was an object.
Prediction. Clean, balanced, no editorializing. In 2021, Loeb expanded the argument into a book, Extraterrestrial, the first sign of intelligent life beyond Earth. It became a bestseller, and the case it made was blunter than the papers. We have spent decades training our telescopes on distant stars, listening for radio signals, searching for biosignatures on exoplanets. All of it rests on the belief that the universe might contain intelligence beyond Earth. And when an object crossed our solar system unexplained, unprecedented, we dismissed the simplest explanation for it because it made us uncomfortable. He wasn't saying it was a spacecraft. He was saying we should have investigated it like it might be, and we didn't. Out of the controversy, Loeb did something concrete. In July 2021, he announced the Galileo Project, a systematic scientific effort funded by private donations to deploy a network of dedicated all-sky telescope arrays specifically designed to detect and characterize interstellar objects and any other anomalous phenomena near Earth, not radio signals, physical objects. The project uses wide-field cameras, infrared sensors, and machine learning classification systems to monitor the sky continuously. The goal is to be ready when the next Oumuamua shows up, not scrambling with existing instruments, not fighting for observation time on overbooked telescopes, but watching and waiting with dedicated hardware built for exactly this. Because the most important lesson from 2017 isn't what we found, it's how unprepared we were. We had 11 days. Oumuamua had already passed its closest point to the sun 3 weeks before we detected it, already moving away, getting fainter every hour. Penstar's data came in October 19th. The world press started covering it October 27th. By then, Oumuamua was at a distance where useful spectroscopy was nearly impossible. If it was a comet fragment from another star, we missed our chance to understand it. If it was something manufactured, we let it sail out of our solar system while we argued about whether to take it seriously. Either way, we weren't ready. The Galileo Project is in part an answer to that failure. Whatever comes next, we will not miss it the same way. Two years after Oumuamua, we got a second chance. On August 30th, 2019, an amateur astronomer in Crimea named Gennady Borisov, building and operating his own telescope from a private observatory, spotted a faint, fuzzy point of light moving at an unusual velocity. 2I/Borisov, the second interstellar object ever detected, and it was completely ordinary. It had a coma, a visible tail. Its spectral data showed water ice, carbon monoxide, carbon dioxide, a normal comet in every observable way, except for the fact that it had arrived from outside our solar system on a hyperbolic trajectory. Borisov answered a question we'd been asking for decades. Does the universe produce normal interstellar comets? The answer is yes. Planetary systems eject debris. Some of it drifts between the stars. We knew it theoretically. Borisov proved it in observation. And Borisov made Oumuamua stranger, not less strange. We know what an interstellar comet looks like. We've seen one. Oumuamua looked like nothing we have a category for. The Vera C. Rubin Observatory in Chile, formally opening its legacy survey of space and time in 2025, is expected to detect multiple interstellar objects per year. Its light collecting power and survey cadence are far beyond anything that existed in 2017. When the next interstellar visitor arrives, we'll see it earlier. We'll have more time, better spectrographs, and, hopefully, the clarity to look at whatever comes without the mix of excitement and overcaution that shaped the Oumuamua response. If it's a nitrogen iceberg, the data will show it. If it's hydrogen ice, same. If it matches no natural model we have, the data will show that too. And then we'll have to decide what to do with what we're looking at. Here's what Objects from other stars have been crossing our neighborhood since before Earth had an ocean, before life existed on this planet. Fragments of ancient planetary systems ripped loose by impacts or stellar encounters, threading through our solar system across geological ages. They came, they passed, they left without anyone here to notice. We've been surrounded by visitors from other stellar systems for our entire existence. We just never had the tools to see them. Oumuamua was the first one we caught. The first one bright enough, close enough, detected just in time to give us 11 days. And when we finally looked at it, when we finally had the instruments and the luck to catch a visitor from another star, we found something we couldn't explain. It came from somewhere we've never been. It moved in ways that broke our expectations. It accelerated without apparent cause, and then it left. Here's what we can honestly say. We need more objects like this before anyone can draw conclusions. One data point isn't science. The natural explanations all have problems, but problems don't rule them out. Science runs on incomplete models. The possibility that it was artificial has not been ruled out by the data. That doesn't make it true, but it doesn't make the question irresponsible. What we cannot say is that we understood it, because we didn't, and it's gone now. As of today, Oumuamua is somewhere beyond the outer solar system, heading toward the constellation Pegasus at roughly 26 kilometers per second relative to the Sun. In the next few years, it will cross the heliopause, the boundary where the Sun's influence gives way to interstellar space. After that, it drifts between stars for millions, maybe billions of years. It came from somewhere we can't visit yet. It went back to a place we can't follow. If this one got under your skin, good. That's what it's supposed to do. Drop a comment with what you actually think Oumuamua was. I want to know. These are the conversations worth having. If you haven't seen the episode on what happens when two supermassive black holes finally merge, it's a different kind of dread, and it's right there. You'll want to watch it. If you want to be here when the Rubin Observatory finds the next interstellar visitor, because it's coming. See you in the dark.